Okay, this is section 4.6. In this section, our goal here is to be able to perform operations with complex numbers. But a little bit of vocabulary, we're going to talk about in this section a new type of number, and that number is I. It stands for the imaginary unit I, and by definition, I is equal to the square root of -1. And also, I squared is also equal to -1, okay? And how we're getting that is because I squared, all that means is I need to take that square root of -1 and square it. But we talked about last section that squares and square roots, they're opposites of one another. They cancel each other out. So we're left with -1. So I squared is -1. That's very important. Okay. We have some properties with these square roots. Okay. If we take the square root of a negative number, and we know it's going to have an I in it because of that negative part in the radicand underneath the square root. So if r is a positive real number, and we take that negative part of r underneath that radicand, or underneath that radical, excuse me, okay, we know that there's going to be an I in there because of that negative. So we're basically pulling out the square root of -1 every time, and we're getting that I. So for example, if I have the square root of -3, I'm pulling out 3 times square root of -1, and we know that square root of -1, that's just I, and the square root of 3 cannot reduce down, so I square root of 3. Also, by that first property there, if I have I times the square root of r squared, it's going to equal the negative of that r value underneath the radicand. So for example, here I have I squared root of 3 squared. I'm going to take that square and distribute it to both of those inside my parentheses. So that becomes I squared. And when again, we take the square root of 3 squared, they cancel each other out and we're left with 3. That's what's going on here. But we know I squared is really just -1. So -1 times 3 is -3. So for example, here, let's try to solve this one. The first thing I want to do is move that 11 to the other side. So we got 2x squared equals -37 minus 11 more is -48. And now I want to get rid of that 2. That's what the x squared. So I'm going to do a division by 2, which gets us -24. And I want to get rid of the x squared by taking that square root on both sides. But remember, we need the positive or negative case of square root of -24 because we're solving for x and we need to consider both the positive case and the negative case. Okay, but if I pull 24 out for a second and I try to simplify that, -24, I know that is the same as -1, and if I pull a perfect square out, times 4 times 6. Okay, but that is just I. Square root of 4 is 2, and the square root of 6 cannot reduce down. Okay, so in the end here, if I simplify that, that's equal to positive or negative I2 square root of 6. Or you could even rearrange it like 2 square root of 6i, as long as i's out from underneath that square root. They all mean the same exact thing. So, again, that tells me I have two answers here. The positive side of I times 2 times the square root of 6, and the negative case of I to square root of 6. They mean the same exact thing, but that plus or minus in that answer tells me I'm splitting it into two separate answers. A little bit more vocab. Since we're dealing with the imaginary unit I, we see these a lot in complex numbers. So a number a plus bi, where a and b are real numbers, and I is the imaginary unit. So a and b are just regular old numbers. So for example, a complex could be 2 plus 3i, or even -4 minus 7i. Those are complex numbers. They have to have a regular old number out front, a real number, and then the imaginary part tacked on the end. So an imaginary number is just a complex number where b does not equal zero, So the imaginary part is always having the I, and the number out front, that's always the real part of the complex number. So to kind of help you visualize the system here in our set theory of numbers, we have all real numbers, which is like the negatives, the positives, fractions, decimals, rational and also irrational numbers. Okay? But another subset of the number system is what we call the imaginary numbers, and they include complex numbers that we just talked about. And a subset within the imaginaries is what we call the pure imaginary numbers. So just having that imaginary unit tacked on and not having that real part A in the beginning. So with this section, our goal here is to be doing operations with complex numbers. So adding, subtracting, multiplying, dividing. So if we want to add them or take the sum of two complex numbers, what we're going to do is add the real parts together and then separately add the imaginary parts together. That will give us a new complex number. Same thing with subtraction or finding the difference. We're going to subtract the regular old real numbers out front and then subtract out the imaginary numbers. That will make a new complex number. So let's try one of these. If I want to add these two complex numbers, again, we're just going to add the real numbers together. So 8 and 5 do make 13. And then if I add the imaginary parts together, there's really a negative 1 right here. So negative 1 plus 4 is 3i. And that's it. That's my new complex number. And I always write it to where my real part goes first and my imaginary part is the second part. In example B here, we're going to subtract them now. So if I combine my real number with the real number, 7 minus 3 is 4. And if I be careful with the i's, or the imaginary part, negative 6 minus negative 6 more, okay, is 0. So 0i. Well, 0 as the imaginary part just makes it 0 completely, or that's just 4 plus 0, or 4. So it is possible to just get a real number. Okay, a real number is a subset of complex numbers. And finally here with example C, what I'm going to do is I'm going to take that negative and distribute to the stuff inside the parentheses so I can get that taken care of easily, which basically just changes the signs on those two numbers on the inside of the parentheses. And again, I'm going to combine my real number, so that makes 4. And my imaginary part's negative 7 plus 4 is negative 3i. And that is it. There's my complex number. So thus far, we just added and subtracted complex numbers. So now we're going to multiply complex numbers, okay? And we do this normally in two different ways, either using the same old distributive property or just using plain old FOIL. So for example here, what if I wanted to distribute that 4i to both of these things on the inside? Okay, so 4 times negative 6 is negative 24, and since I have I there, it's kind of acting like a variable, so I'm going to keep it there. And then if I multiply 4i times 1i, well, 4 times 1 is 4, but I times I is I squared. Okay, it's kind of like variables. When you multiply x and x, that makes x squared. But we just talked about at the beginning that I squared was special. So I'm going to box that up. I always try to do that and make that a negative 1 because that's very important to pull out, which basically turns the sign on the number out front, okay, to its different sign. And what I'm going to do is pull that number out front, so it will become a negative 4 when I change its sign. And I'm going to write the imaginary part last. So there is my complex number where the real part is in the beginning. Okay. Then, if I want to multiply two complex numbers together, okay, I am going to use FOIL. So, if you remember what FOIL is from a few sections ago, It stands for first, outer, inside, and last. So I'm going to multiply my first together, and that makes negative 36. And then my outside stuff. So 9 times 7 is 63. I. Then I do my insides. Well, negative 2 times negative 4 is positive 8i. And negative 2 times 7 is negative 14. But these had two i's, so I squared. And if I pull out I squared, that was special. That was negative 1, which flips the sign on my negative 14. And how I'm going to write this as is by moving it up here with the negative 36. So it changes to positive 14. And I'm recopying down my I stuff. It's just going to make it easier on me to combine here in a second. Because negative 36 and 14, that's negative 22. And 63i and 8i make 71i. And here's my complex number out of that. So we multiplied, we added and subtracted, and now all we have left to do is divide. Okay, divide our complex numbers. Okay, and we use this with conjugates like we did in the last section. Okay, same kind of deal, but instead of a square root, we're dealing with I stuff. So for example, if I want the conjugate of 4 plus 3i, okay, we're still flipping the sign in the middle, so 4 minus 3i. And we're going to do the same kind of exact method as with the square root. We're going to multiply the numerator and denominator by that conjugate of that complex number in the denominator. So for example here, if I want to get that imaginary complex number out of the bottom there, I'm going to multiply by its conjugate, or 1 plus 4i. Okay, so over here it'll be 7 plus 5i times 1 plus 4i, because I always multiply numerator with numerator, and straight across in the bottom as well. So 1 minus 4i and 1 plus 4i. But if you see here, we're going to have to FOIL twice. So let me FOIL the top, or the numerator, first. Okay, so 7 times 1 is 7, and 7 times 4 is 28i, and 5i times 1 is 5i, and 5 times 4 is 20i squared. And again, if I pull I squared out, that is equal to negative 1, which flips the sign on the 20. And if I move that together with 7, that will help me out. So 7 minus 20 is negative 13, and 28 and 5 make 33i. So here's the top part. Okay, then the bottom, I'm going to need the FOIL again. So 1 minus 4i and 1 plus 4i. So 1 times 1 is 1. 4i times 1 is 4i. Negative 4i times 1 is negative 4i. And negative 4i times 4i is negative 16i squared. Again, pull the I squared out, which changes the sign on the negative 16 to positive 16, and bring down the i's. Well, 4i minus 4i, that's 0, but 1 plus 16 is 17, and that's going in the bottom here. Okay, so here is my simplified version of those complex numbers being divided by each other. I could also break this apart as negative 13 over 17 plus 33 out of 17i. They mean the same exact thing. This is just in the complex number form. So not only can we add, subtract, multiply, and divide complex numbers, what we're going to do is actually graph them too. But we're going to actually put them on a different kind of plane where we switch up the axes a little bit. The vertical axis is now going to be called the imaginary axis, and the normal horizontal x-axis is going to be called the real axis. So let's look at how we can actually graph complex numbers. Okay, so we just said, well, the normal x-axis or horizontal axis is the real axis, and our typical vertical axis, or what we normally call the y-axis, is called the imaginary. So this is the real number part out front, and the imaginary axis is the I part. So if I'm going to graph 3 minus 2i, I'm going to go 3 on the real axis and down 2 on the imaginary, and that is A. It's kind of like thinking 3, negative 2 on our normal plane. If I want to graph B, that's negative 2 on the real axis and up 4, and that's B. Or if you want to think about it as negative 2, 4. C, though, I don't have any real parts. I'm going to start at the origin 0 and go up 3 on the I, or imaginary axis. So that's C. And that was kind of like saying 0, 3. And the last one, negative 4, negative 3. And that is D. Or like saying negative 4, comma, negative 3. So you could plot them all on the same coordinate grid or complex plane, but just know that your imaginary axis is now the y-axis, okay? And the real axis is now your x-axis. And lastly here we have that we can take the absolute value of a complex number. And the only thing we need to do is look at the A part, or the real part, and the imaginary part, square those numbers, and put them underneath a big square root and simplify. Okay, so let's look at how we can take the absolute value of a complex number. So if I want to take the absolute value of negative 4 plus 3i, my A part is negative 4. And make sure you put parentheses around that negative 4, or else it might give you a wrong answer. And then we're always going to add. No matter what symbol is here, always add underneath that square root the number attached to your I, or the imaginary part. And if you simplify this, negative 4 squared is 16, and 3 squared is 9. But we know 16 and 9 make 25, and 25 underneath the square root is actually 5. So the absolute value of that complex number is 5. In our last example here, if I want the absolute value of this complex number, okay, I don't have any real part, so I'm just going to make it 0 squared. Always addition underneath there. And then our imaginary parts number, which was negative 3, and we're squaring it too. Well, 0 squared is 0, and negative 3 squared is 9, and 0 and 9 make 9, which is the same thing as 3. Okay, so in both of these examples, it did equal out to be a regular old whole number. But it can still be the case, though, to boil down and get to like the square root of 3 or square root of 2. Something that cannot simplify all the way down perfectly. So it is okay to get an answer that looks like square root of 2 or square root of 3 when you do take an absolute value of a complex number.